Oh, good for you. So proud. Okay. I'll be here. Okay, let me just talk a little bit about what's coming up. We've got Green's theorem today. We're going to introduce two new operators on Wednesday called the divergence and the curl, which will get us some notation that we're going to need for this week following Thanksgiving, where we introduce Stokes' theorem, which is a theorem about the curl, and we introduce the divergence theorem, which is not surprisingly a theorem about the divergence. But before we get to those important theorems, we do have to talk about divergence and curl, and then we do have to talk about parametric surfaces, in other words, how to do surface integrals. And this is different from the surface integrals that you did on the last exam. Today we introduced the first of these three great theorems that I keep talking about, Green's theorem. Green's theorem, divergence theorem, Stokes' theorem are the three big theorems that I really like from this material. And Green's theorem is it's one of the earliest theorems of the larger field of differential geometry, where you connect calculus to geometry in a way that you don't normally do. Like, you remember when you did geometry back in high school, and you had triangles and right angles and side angle side and all that sort of stuff, and there wasn't an integral or a derivative in sight. Okay? Well, it turns out that if you want to bring those tools into the geometry classroom, you can do that, and you can get some very powerful results using calculus to explore geometric objects. And Green's theorem is one of those really powerful results. All right, before we do that, though, any questions on what you're working on right now, what you're turning in? Lila.
On the leopard, on number 4, how are we supposed to know by looking at it if it's conservative?
Let me look at it first. Which one, 4?
Yeah.
Oh yeah, this is a good problem.
Let's try this one.
Okay. There's a few things. This lesson actually pulls in a few different ideas. One of the things that we know about conservative fields is if we compute the work integral around a closed path, you get 0, right? Okay. Do you see, let's look at this first one. Do you see a work integral, a closed work integral path where you're not going to get 0?
If you go a circle in one direction.
If I go in a circle around the origin, right? For example, let's go clockwise around the origin. You see that the motion is always with the force, which means positive work. And that's true all the way around, so there's nothing to cancel. Like if I go along this stretch here, I get positive work, positive work. The only way that I'm going to undo that positive stuff is if I balance it out with some negative work, which there's no way to do. So immediately I know that the first graph is not a conservative field because I can find a closed work integral that's not 0. That's 1. Let's talk about 2. 2, what I want you to start thinking about now is the test for conservativeness. Okay, so let's remember we have a vector field whose coordinate functions are p and q. To test that thing for conservativeness, we want py equal to qx, right? Py equals qx. Okay, keep that in mind, and now let's stare at this vector field. And tell me something about p and q in this vector field. In the second one in the middle, the top middle. Go ahead, Greg.
Q is always 0.
Q is always 0, I agree.
P changes with the x.
It does. Does P have any y dependence? P has no y dependence. Those are two important facts. So Q is 0 and P has no y dependence. So what's the partial of P with respect to y? 0. And what's the partial of Q with respect to x? 0. Okay, let's keep going. This guy is really just this picture rotated. So if that one was conservative, the other one is conservative. But you can make the same argument, right? So here the reverse is true. You see P is 0 and Q has no X dependence. Yeah? Okay. So conservative. How about this guy? It's conservative. Make an argument.
There's no dependence on either vector.
Yeah, this appears to be a constant vector field, doesn't it? At every point, we're attaching the same vector that points down and to the right. At every point. So that means P is a constant, Q is a constant. Py equals Qx equals 0. Conservative. Let's keep going. Bottom middle. What do you think? Another thing about conservative work vectors is they're independent of path. So can you find 2 points where the work along one path is clearly positive and the work along another path is clearly negative? Yes? No? Maybe? Can you give me an example?
A circle on one path, a circle, like 2 semicircles.
What 2 points do you want to go to and from?
Like halfway up.
Okay, so we'll go like from 0, 2 to 0, negative 2. Good. And then a semicircle in that direction is probably going to be positive, right? If we go from here down to here, it's going to be positive. On the other hand, if we go from here down to here along this way, it's probably going to be negative, right? Because I'm going against the force. Okay. How about this guy? Conservative, not conservative? If it's not conservative, can you give me a path that will convince me? Yeah, go ahead.
Well, I would say it's not conservative because if you picked like 2 opposite corners and you went like, if you were starting at the top left going to bottom right, you could go just straight down and then to the right, and then that would be like positive.
Like that, and then to the right, good.
But if you went across and then down, it would be negative.
Does everybody see that? Okay, so I want to go from this point down to this point. Okay, the first path that Hannah suggests is to go down. Now that's all 0, right? Why? Because they're perpendicular. And now this is all positive because I'm going with the force and I'm there. Okay. Now I'm going to start here and I'm going to go in this direction. That's all negative because I'm going against the force. And that's all 0 because I'm going perpendicular. Okay. I like that problem too. Like I said, I'll try to get some of these on the next exam. Okay, other questions? Good. Okay. You guys are vastly superior to the 1 o'clock class. Oh wait, I recorded that. I didn't mean it. Okay. Yeah, go ahead.
It might be more of like a personal thing, but I had trouble going from, in the most recent section, finding F. So I was fine with showing that the partials were equal, but then finding an F from there. I mean, it's probably not something that everyone needs to do.
Okay, well, yeah, if you wanna bring some problems to me
Okay.
after class, we can certainly do a few examples. Your head definitely spins on those, especially with the 3-dimensional ones. How many have done some 3-dimensional ones? A couple of you. Okay, make sure that you get those squared away too. And the better you can do the 3-dimensional ones, sort of the easier the 2-dimensional ones are. Okay. Today, Green's theorem. I'm not going to prove Green's theorem. The book actually goes through a fairly simplified proof of Green's theorem. I don't feel like it's really illuminating any of the topics in the section. It's a proof because it needs to be there because it's a math book. So look over the proof. It uses some simplified geometric examples and essentially the fundamental theorem of calculus. what I'm going to do is simply state the theorem, talk about some of the geometric implications of the theorem, do a few examples, and then we'll be on our way. So 16.4. Green's theorem. Here's the picture that I want to, some notation and a geometric picture that I want you to carry around in your head. We're going to be talking about sets D in the plane. And we're going to be talking about the boundaries of those sets oriented in the counterclockwise direction. Let me close that off a little bit there. And then I don't know how to ignore that. Okay. So we're interested in D and its boundary. The boundary is just a curve like you've already explored in line integrals. And in fact, it's even a specific example of a curve. The boundary of such a set is always going to be a closed curve. Right? Okay. So this is a closed curve. Around D. This is also often called the boundary of D. Although there's a little bit of subtlety with the orientation of the boundary, but I don't want to get into that now. We're going to talk about the boundary being a path that you traverse in the counterclockwise direction. And then some notation. Often denoted with the partial symbol. That's the same symbol that you see in the partial derivatives, except we put it in front of the set D. And that means whenever I put the partial symbol in front of a set, what I'm talking about is the boundary of the set. This is a very general piece of mathematical notation. If you go on in mathematics, you'll certainly see it again. And it's not just for two-dimensional sets. For example, the boundary of an interval AB. What do you think the boundary of the interval AB is? A and B. Okay, but it also lifts up to 3 dimensions. You can take a solid, for example, a solid sphere of radius r. And then I can put the boundary operator in front of it, put the partial thing in front of it. And then what I'm talking about is the shell, not the inside, but the shell. So we have this very generic way of, when we're talking about a set, we can put this partial symbol in front of it and immediately start talking about the boundary of the set. Great.
So the partial symbol with D next to it is exactly the same thing as C.
There's a subtlety. The partial symbol with D after it is the set of points, but there's no orientation.
Okay.
And C is oriented. We will often blur those lines in this class, blur the lines between the fact that the boundary of a set is typically not oriented. It's just a set of points. But we'll often just say, take the boundary of the set, oriented counterclockwise. Okay. Good. So that's a little bit of notation. Let's set up some objects of study. Let's let F be a vector field, just a two-dimensional vector field for now. We won't talk about three-dimensional vector fields until Wednesday, I guess. Let F be a vector, a differentiable vector field. What differentiable, all differentiable means is that Px, Py, Qx, and Qy all exist. So let F P equal PQ be a differentiable vector field on the set D. And I'm not going to really get into the specifics of the set D other than to state that it's a nice set. Not sect, but set. It's a nice set, meaning that it's bounded. A bounded set is one that doesn't have any parts that go off to infinity. Or a better way to say it is a bounded set will fit inside of a circle of some radius. I can find a circle big enough to contain the set. That's a bounded set. But more than that, it's not, it doesn't have strange properties. For example, has anybody ever heard of the Mandelbrot set? Maybe you have? Have you heard of fractals? Okay. So one of the things that mathematicians have to deal with all the time are, we have to be very precise. There are often exceptions to the theorems that we prove. And the Mandelbrot set is often one of those exceptions. This is a perfectly lovely bounded set. In fact, it fits inside of a circle of radius 2. But the boundary of this set is a disaster. The boundary of this set is so messed up that it is neither one-dimensional nor two-dimensional. But in fact, it has a dimension somewhere between 1 and 2 dimensions. That's how bad the boundary of this set is. In fact, that's where fractals get their name. This is a fractal. And where fractals get their name is they occupy dimensions that are between whole numbers. So the boundary of this set is between a one-dimensional and a two-dimensional set. What does that even mean? That's for another class. So when I say a nice set, I mean just something like this, okay? Not like that. So in a universe where we admit the possibility of having Mandelbrot sets, I have to be careful because Green's theorem gets a lot more complicated on the Mandelbrot set. Okay, so we have a differentiable vector field, and we have D, which is a nice set, and now we at least have an idea of what a not nice set is. Okay, well, let's see. Well, let C be the boundary of D oriented counterclockwise. So if I'm looking down on D, then it goes counterclockwise. Why counterclockwise? It really probably goes all the way back to the fact that we take our thetas counterclockwise in the unit circle, right? And it's an arbitrary choice in much the same way that theta is counterclockwise in the unit circle. That could have gone the other way. We just chose to not do that. All right. So it's a worldwide standard to talk about counterclockwise oriented boundaries. Okay. All right. So we've got the boundary of D oriented counterclockwise. I think we have all the pieces in place to state the theorem. The theorem goes like this. It says that the integral over the region D of q sub x minus p sub y dA is the same as the integral around the boundary of p dx plus q dy. And that's the main result. That's Green's theorem. Stare at it in all of its glory. I think glory is probably pushing it, but I think one of the striking things about this is that it relates an integral around the outside of the set to an integral over the whole set. And that's really unusual. Let's look at some of the consequences of this thing briefly, and then we'll get into some computation. So there's an interesting geometric consequence of this that follows from so there's a relationship between the area and the perimeter of D. Here's a question. Can you find P and Q so that QX minus PY equals 1? Can you do that? You have a lot of freedom, right? P and Q are just functions of X and Y, so they can be anything you like. Can you find any P and Q so that QX minus PY is equal to 1? I'll let you chew on that for a minute. Can you think of... You're nodding your head, Lane. You have one? What is it? So Y and 2X like that. So QX is 2, PY is 1. Yeah, I'll buy that. Any others? You could make one of them 0. For example, if we make P equals 0, what's Q have to be? X. You could make the other one 0. Negative Y, good. And then another crowd pleaser or crowd favorite is the following. You'll see this one probably most often in the literature. All of these are important. Even the first one that Lane came up with, I've seen people use that one as well. Exactly. Yes. Not in the encounters literature. Yeah. Yeah. You'll find it in the Odyssey, chapter 32. Okay. Trying to make sure I get my signs right here. Yeah, so any of those pairs will accomplish this goal. Well, why is this an interesting goal? Well, let's see the consequences of this. I'll use the last pair since, like I said, it is probably the crowd favorite. Drop that into this guy, you get 1 dA. After all, that was by construction. And you put that over here, oops. P is minus y over 2 dx, and q is x over 2 dy, like that. Now, what is this thing on the left-hand side? The integral of 1 over d dA. It's the area of D, which I'll write like this. So what we see is that the area of D is equal to this integral on the right-hand side, which I'll write in a slightly friendlier way also. Oops. And you get this interesting geometric formula, right? If I ask you what's the area of a circle of radius r, what do you tell me? Pi r squared, right? If I ask you what's the area of this guy up here, well, I don't really know, but I can represent it as an integral like this. or using any of these other pairs that we came up with. Any of these other pairs will do, but this is probably the most popular one. What I've just come up with is an integral formula for the area of a plane figure. The connection between geometry and calculus. One of the earliest known results, actually, between well, I mean, there's the big one, right? The area under a curve between A and B, right? Yeah. But this is somewhat more advanced. This is, gosh, probably 200 years after Newton. Newton did all of that stuff. Maybe not 200. Let me think a little bit. But at least 150 after Newton was doing his stuff. Then you get this guy. Okay. And, you know, this is not how you're going to be using Green's theorem. We're going to be using Green's theorem in two main ways. One as a computational device. So if you have a line integral, let's go back up and look at the main result. If I have a line integral, like on the right-hand side here, I can turn it into an area integral, which may be easier to compute. Or if I have an area integral, which is the left-hand side, I can turn it into a line integral, and that may be easier to compute. So that's one way that we're going to be using it. And the other way we're going to be using it is to, in theory, using proofs and things like that. And I'll talk a little bit about that after I do some examples. So the remainder of today, what we're going to do is some examples of applying this thing, and then I'm going to pull out two interesting results, interesting theoretical results that follow from Green's theorem. So let's do a calculation just so you can see how to use this in practice. So I want to start with 16.4.2. And so we have this line integral, the integral over the boundary of D, and the assumption here is, again, the book is kind of being loose, but the assumption here is that you've oriented the boundary of D in the counterclockwise direction. D is just a square of side length 1 with one corner at the origin. So let me try to copy that faithfully over to the other side here. xy dx. And was it xy dy? Thank you. And then D was this figure in the plane. Now, as a line integral, you could do this. It wouldn't be fun, but you could do it. Why not fun? Because there would be 4 pieces to this line integral, one for each side. And you would parameterize the 4 pieces, and you would just crank through the 4 integrals. And when you were done, you would add them together, and you would have the answer. And this, frankly, is the motivation for using Green's theorem, is that's a computationally intense process, and maybe we can replace it with an area integral that's a little less computationally intense. So go back and look at the form of Green's theorem. So I'm looking at the right-hand side. That's what I've been given. I want to identify P and Q so that I can build the thing on the left-hand side. And if you look closely here, P is the thing on the dx term, and Q is the thing on the dy term, right? So that's the big hint for how to figure out what is what. So this guy is P, this guy is Q. So P is xy, and Q is xy. By Green's theorem, we know then that this integral is the same as the integral over D of qx, which is y, minus py, which is x. Right? I don't know, is that an easier integral? It could be. What are the limits of integration for this guy? 0 to 1, 0 to 1, good. The order of integration? Doesn't matter, right? Not in this case. So take your pick, 4 line integrals or this one double integral? I would take this one. Okay, let's do this one. 0 to 1, y minus x dy. So the inner integral looks like this. If I plug in 1, I get 1/2 minus x. If I plug in 0, I get nothing. The outer integral looks like that. And that gives me 0. Certainly, I think, faster than doing the 4 line integrals. Even though those 4 line integrals are actually not that difficult. We should check our answers here. 16.4.2. Yeah, okay. Questions about that? Okay, let me do one more example before I go back to the theory. I want to go down and do 11. So 11 is not anything really more complicated than the other one. The thing I want to emphasize with 11 is when you get to that area integral, then you're free to pull in all of the things that you've learned about doing area integrals up to this point. So you can probably guess where 11 is going to go when I convert this to an area integral. I'm going to end up doing polar coordinates. But just to reassure you and show you how that works, let's do this. So number 11 here, we've got x squared y minus xy squared. And the region of integration was just the unit circle. Yuck. It's a little better. Okay. What's the first thing? If I want to apply Green's theorem, what do I have to do? I have to identify P and Q. So P is the coefficient on the dx, and Q is the coefficient on the dy. Careful here with Q. What is Q? Negative xy squared, exactly. Right, if you look in the statement of Green's theorem, there's not a minus sign in Green's theorem here, there's a plus sign. So that means that minus sign must belong to the Q. Okay, let's compute P sub y and Q sub x. Also suggestive of polar coordinates. And let's integrate over d qx, which is minus y squared, minus py dA. Definitely looks like a polar integral. Right? And there's no theta dependence, so I can do the theta integral right away. Oops. Go away. Go away. There. And theta integral's already done. And I can finish this off relatively quickly. It's negative pi over 2, whatever that means. So when you get to that double integral, you're then free to use whatever tools you want to evaluate the integral. Okay? Questions about that? All right. So let's talk about some of the theoretical applications of this thing. So theoretical applications of Green's theorem. So I'm going to rewrite it here just so we have it in front of us. So that the integral over d of qx minus py dA is equal to the integral around the boundary, oriented counterclockwise, of p dx plus q dy. So that's Green's theorem. If F is a conservative vector field, F equals P comma Q. What do we know about the relationship between P and Q? If F is a conservative vector field, the test for conservativeness,
Px equals Q.
Py equals Qx. So, what does that tell us about the left-hand side of Green's theorem? It's actually 0. Okay, if I integrate 0, right, think of it, why, I see your confusion, right? So some people are saying constant, right? And clearly the antiderivative of 0 is a constant. But that's for antiderivatives. This is an actual definite integral. This is the definite integral of 0 over the region D, which in our minds geometrically means it's the area, the volume under the surface, z equals 0, and that's 0. Okay, so the left-hand side of this guy is 0. The right-hand side is the boundary of D. So for a conservative vector field, this is true. Now, you may recognize this thing from back in section 16.2. Maybe not. What's another way of writing that line integral on the right-hand side? F dot dr, exactly. Oop, yeah, well, we'll just get rid of that. Which is work, right? So if F is a conservative vector field, then Green's theorem shows us that this work integral is 0. Now, does that mean that every work integral is 0? What's special about Green's theorem and this work integral? It's a closed path, right? And how do we, how is it closed? How do we know it's closed? It's the boundary of this nice bounded set, D. So that's a closed path. So here's a way of getting at this closed path thing. Okay, let's do another one. What else do we know about conservative vector fields? Work integrals of conservative vector fields. So Green's theorem would seem to not be able to say much about this particular property, right? Because Green's theorem always needs a set and a closed curve. And this thing here, work integrals of conservative vector fields are independent of path. Those paths may or may not be closed, right? It's just really, it's just saying that the work integral just depends on where you start and where you end up, which is more general than the whole closed path thing. But in fact, Green's theorem does say something about independence of path. Let's look at a situation here in the plane. And let's pretend that F is a conservative vector field. Let's take a start point A and an end point B and look at some path between them. Let's call that C1. Okay, we can write that guy. We can write that guy as the integral C1 f dot dr, right? That's the work. Independent of path. Well, let's see if we can somehow convince ourselves of that. So let's put in another path. Like that. And we'll call that C2. If I put in another path like that, I don't really care what it does. If I put in another path like that, I'm going to actually create that path with the first path actually encloses a region. Right? And if I build, what's the boundary of this thing?
C1, C2.
It's kind of C1, C plus C2. There's an orientation problem, right? So I can go around the boundary here if I go along C2 and then go backwards along C1, right? And the way that we write that, so the CCW, that's counterclockwise, the CCW boundary integral, or path, around D is first is to go along C2 and then back C1. We actually have a notation for that. It's not in the book, but we do have a notation for that. What we will call that path is C2 minus C1.
Is that just notation, or does that work algebraically?
It actually does work algebraically, so you get some nice, again, not in the book, but let me just show you a couple of things that are true. For example, the integral along C of f ds is the same as minus the integral along minus C f ds. So if I do a line integral along C, and then I do the same line integral along the reverse of C, I introduce a minus sign. This is absolutely equivalent to regular old Calc 2, where if you integrate from A to B, it's the negative of integrating from B to A. It just happens to be along a curve. And then another result is if I integrate along a composite of paths, that's the same as integrating along the first path, and we've already kind of encountered this. plus the integral along the second path. Okay, and that's exactly the same. If I integrate from a to b, that's the same as integrating from a to c plus the integral from c to b. I can break up an interval. Okay, I can break up a path in the same way. So all of this notation hangs together. So suddenly what I have, by Green's theorem, that the integral around c of f dot dr is equal to 0, right? Why is that? C is a closed path. C is a closed path. So now that's precisely an application of Green's theorem. On the other hand, we know that C can be written as C1 minus C2 f dot dr, and that's equal to 0. And you can, not surprisingly, break that up into C1 f dot dr minus C2 f dot dr. And you can run that C2 over to the other side. And what you see is that the path doesn't matter. There are just dozens and dozens of little tricks like this that you can play with Green's theorem. We only get to do a few in this chapter, but really powerful result. It's fun because it again, it mixes these very geometric ideas with calculus in a way that's really kind of fun. Let me show you, maybe see if David has a picture of it somewhere here. Plus a bit of a preview of what's coming. I just can't remember if he has this one particular picture. No, it doesn't look like it. Anyway, all I can say is, again, you've heard me say this before, I teach a class called Complex Analysis, which will run not this spring, but next spring. And in that class, you play a lot of really cool games with these kinds of paths. For example, I'll just draw you one. So you can have like a little place that's bad, and you can build a little circle around it. And you can have this contour integral that goes around the outside, and then you can go in to that guy, and you can go around it. Let me make sure I get the directions right. And then back out like this. And then this guy can go in like this and around, and then back out like that. And you get some really clever constructions using Green's theorem and carefully constructed paths. And you can sort of go around bad spots in the domain and so forth. And these guys cancel because this path is the exact opposite of this path, and this path is the exact opposite of that path. And you end up getting that the integral around the bad spot in the clockwise direction is equal to the integral around the whole domain in the counterclockwise direction. Lots of fun stuff comes out of this. And we do a lot of that in complex analysis. So just the tip of the iceberg, I guess, is the moral of that story, that there's a lot to Green's theorem. Let me just briefly walk you through web work. I don't think there's anything dangerous in there, but let's just have a look. Fundamental theorem of line integrals. Let's go here. So that one, no problem. This guy, same deal. Yeah, this one. This is the one I wanted to talk about. So find a parameterization of this curve and use it to compute the area of the interior. So this goes back to that area-perimeter relationship that I derived earlier. The reason I stopped at this one is I want to give you a hint as to how to find the parameterization of that curve. If I asked you to parameterize this curve, one thing that you might try is x equals cosine theta, y equals sine theta. And if you plug those in, it actually satisfies the equation, right? So my hint for this web work problem is, wouldn't it be nice if this were just squared and squared? So see if you can come up with a parameterization based on sine and cosine so that when you drop them in there, it turns into sine squared and cosine squared. That's my hint. All right. Let me see if there are any other. I think that one's okay. A lot of moving parts, but okay. And this one, okay. So you're given this vector field F, and you're asked to consider F around the circle of radius A. Find the line integral for A equals 1. So you don't want to do the line integral. You want to do an area integral. Actually, it's your choice, to be honest. I don't want to force you into anything, at least not for this problem. So you can use Green's theorem, or you can just do the line integral directly, although I think the line integral directly might be painful, because if you parameterize the circle of radius 1 in the usual way, say cosine theta, sine theta, you're going to get like a sine cubed here, which won't be fun, and maybe an e to a cosine, which is also not going to be a joyful experience. And so I'm thinking, yeah, you probably want to turn this into an area integral using Green's theorem. Why? Because ultimately this is p. You're going to be dealing with p sub y, and p sub y is going to get that out of your hair. Okay. So you'll do that for part A. For part B, for which value of A is the line integral a maximum, you're going to want to repeat. In fact, I wouldn't repeat. I would just do it for a generic A, and then let A equal 1 to answer this question, and then see how it works with A more general in B. Questions? All right, I will see you Wednesday.